Sairam and welcome to the next session in computational linear algebra, where we are going to continue our discussion on the elimination strategy. So let us begin this session with a prayer. Om Saishwaraya Vidmahe Satyadevaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. So we have an idea of what is forward elimination and back substitution now, and the two most important points that we learnt were what we call as pivots, right? These are the first non-zero elements appearing in any row, and that is what we call as pivot elements. And the second important point we learned is that elimination leads us to an upper triangular matrix of coefficients, right? Transforms the matrix of coefficients to an upper triangular matrix. And the interesting part is the pivots are on the diagonal. On the main diagonal, they appear in the upper triangular matrix. After that, we use back substitution and then we find the solution for that linear system. And remember, we have done this only for a n by n system. We always had n variables and n equations, or should I say n equations and n variables. We have never worked with unequal number of variables and equations. So right now that's not the agenda, therefore we will see that later. And we said that in this session we want to look at how elimination could fail, right? Are there cases where elimination could fail? So before I step into that, I thought there could have been a question from the last session where we discussed about the order of the computations of the floating point operations being used in elimination. So let me quickly give you a rough idea of how I am calculating that. So remember that in the strategy to eliminate so this is how we had drawn. Remember that we said that we will first start by trying to eliminate this element, which is the first element in the second row. Okay, and we have to an1, ann, right? So the first part of the strategy would be to eliminate this, and then rest of the elements also below in the first column, except for the first element in the first column. And each of these are row operations, which means that there are n floating point operations straight away here, because you need there are multiplications and subtractions happening, and both multiplication and subtraction together I am taking it as one floating point operation. Okay, and like this, so that for one row operation we are doing n here, right? So n we are able to do, and like this we are performing n minus 1 row operations, right? So we have n minus 1 into n for n minus 1 into n floating point operations for eliminating a21 to an1. Okay, now for the recursive matrix, which is n by 1 by n by 1, again we look at this element as the pivot and try to eliminate the elements under this in the second column. Now the floating point operations would not consume n operations, but they will just consume n minus 1, because one column is not there. So for each of those we are actually spending n minus 1 row operation, n minus 1 floating point operations, and like that we are doing it for how many different times are we doing the row operations. So except for a22, everybody else, which means that there are n minus 2 row operations. Therefore this would become n minus 2 times n minus 1, right? We can continue this, and finally you will reach a point where I just need 2 floating point operations, that's the last 2 by 2, and I need 1 row operation. So this is how it will terminate. So if we take a look at this expression, one thing for sure is that there is an n square term. Of course there are subtractions of minus 3n and some constants which are getting subtracted, but we remember that we are looking at the big O notation, and we are having n square in each of these terms till the end. So this is like saying I have an n square here and in the next one also I have an n square, so on. And remember that we are adding it at least an n minus 1 times, right? So therefore effectively this is going to touch order of n cube, right? So that's one clarification that I wanted to add in this session. So now let's proceed and see, is elimination going to be a great strategy in every situation, or are there situations where elimination fails? Okay, here is a linear system of equations. We have two equations and two variables. We are on R2. Let's try and perform elimination on this. So what I'll do is I'll just put them down as matrices, because we now are accustomed to using matrix as a unit. So we have a 1 here, a -2, 3 and a -6. Okay, what's the strategy? We have to make this 3 to 0. Therefore, what's the pivot? Pivot is 1. So I need to take this coefficient divided by 1. So that's the multiplier, that's 3. So what is the row operation that we want to perform, right? So we are saying we want to change row 2. Row 2 is going to be set to row 2 minus 3 times R1, right? How did I get this? This coefficient divided by this pivot, and that's this multiplier. Okay, so let's do this operation. This will not change it will not change the first row, so let it remain like this, 1 and -2. And let's do the subtraction. 3 minus thrice of this, that's going to be 0. -6 minus thrice of this, -6 minus -6, oh god, that is 0. So that's the coefficient matrix now. Okay, now you see something interesting that's happening. There is no second pivot, right? There is no second pivot at all. Okay, let's try and do this also in the right hand side. Let's perform this operation also on the right hand side. So when I have 1 and 11, and if I perform the same operation here, let's see what we get. So 1 will remain the same, 11 minus thrice this, and that's going to be an 8. Okay, now let's take a look at what do these equations actually convey to us, right? So look at this matrix on the right hand side and let's see what kind of equations form. In effect, what it says, it gets transformed to saying x minus 2y equal to 1. The second is a 0x plus a 0y is equal to 8, right? And what is this? This is actually a 0, and we are saying 0 equal to 8? No, right? That means that there is some inconsistency in this linear system of equations, right? And therefore this system of equations may not have any solution, right? There is no solution. Okay, so elimination did not help us find the solution, but at least it took us to the place from where we are able to determine that there is no solution, right? And what is it that we are observing? We are observing that when we actually used elimination and found a solution, for n by n we always had n pivots. Remember that in the last session we had 2 by 2 we had 2 pivots, so 3 by 3 we had 3 pivots, n by n and n pivots. But here we have a 2 by 2 system, but we have only one pivot, right? So just let's just keep this in mind, and I will show you one more example. So here is one more set of equations. Look at these, they are almost the same equations except for the right hand side that we have modified. So I pick up the coefficient matrix, same row operation, no change, and we get this same answer here, right? 1 minus 2 0 0, exactly same here. But let's look at the right hand side now. It's 1 3, and if we perform R2 minus 3 R1, set R2 is going to become 3 minus 3 times 1, which is 0, right? So this is what we get. Now let's see what the equations tell us. So if you take xy and try to multiply here, we are going to get the same equation first. It's going to be x minus 2y equal to 1, that will remain the same. The next one is going to become 0x plus 0y is equal to 0, right? So this is saying basically 0 equal to 0, and there is no inconsistency here, is it not, right? There is no problem here, right? This is fine. And therefore what is the problem here? The problem is that we have two variables, but there is only effectively one equation, which means this one has got infinite solutions. How do I say it has got infinite solutions? I'm going to pick up a y and find the x for it, right? For example, let's say I pick y equal to 2. then I can pick x equal to 5. If I pick y equal to 1, so let me just write this down, infinite solution. So you could choose either way, right? You can fix the x and then find the y as well. It doesn't matter. It will all eventually lead to the same solutions. So I said if y is equal to 2, then x is equal to 5. If y is equal to 1, then x equal to 3, and you can keep going on, right? You can keep changing y however to any value, and you will definitely find an x for it, and that means that it has got infinite solutions. Now look at something interesting again. What is elimination showing us? It is again leading to no second pivot, right? And we are actually left with a single pivot. So that's interesting. So let us try and then summarize the systems of equations, and we will be able to classify now to understand when does it lead to no solution and infinite solutions. So this is the way that we are going to summarize this. We are going to say if I have an n by n linear system of equations. So when I say n by n, you must remember that we are talking about n equations and n in n variables. Okay, what we do first is we first do elimination and look at the upper triangular matrix and ask if there are n pivots or not, right? Now this is the crucial question, and if there are n pivots, right? So let me write down here saying yes, there are n pivots, then we call this system of equations as non-singular, and in non-singular we are going to say it has got one solution, right? It will have a specific single solution, and it is something like saying looking at two intersecting lines in a single point, and that becomes the solution. Suppose we don't have n pivots, right? Suppose we say the answer to this question is no, then we are going to call this system as singular system of equations, right? So there's some issue here. When you say singular, there's got to be some issue here. But under singular you have two cases. One is that you may land up in no solution, or you may land up in infinite solutions. Okay, how do you figure this out? We will have to look at those equations and see if the right hand side is matching to the 0 of the left hand side, right? So typically you're going to land up in singular means that, you know, we are lacking some pivots, which means that 0 elements are coming, which means we also perform the same operations on the right hand side. And like in the previous case, if we find that the right hand side is inconsistent, we know that there is no solution. But if the right hand side also comes out to be 0, which means it is quite consistent, and therefore it will lead to infinite solutions, right? So this is the simple picture that we must always keep in mind. The idea is that we may land up not just in, elimination doesn't lead us always to a solution case. It can help us also find if there is no solution or there are infinite solutions. So what we'll do next is we will look at each of these cases a little graphically and try and understand how those pictures relate to these three different cases. So here we are with our pictorial representation. So this is our first problem that we solved in the last session, a 2x2 case. We picked up these two equations and we used elimination and solved for the answer. We remember the answer we got was I think x is equal to 3 and y equal to 1, right? Now let's look at what happens in pictorially, right? Okay, so we pick up this equation 4x minus 8y equal to 4 and try to draw this, and you can see the one in blue here, right? So with a positive slope, that's the one that represents this first equation. Okay, now the second equation is here in yellow, that's 3x plus 2y equal to 11, right? And very interestingly, we can see that they intersect at this point 3, 1, right? So at 3, 1 they do intersect. But what's more interesting is elimination does a row operation and brings up two other equivalent equations, first of which doesn't change, 4x minus 8y equal to 4, which means this blue line remains the same, but the second one changes to 8y equal to 8, which is essentially y equal to 1, and that's this interesting line in green which passes parallel to the x-axis, right, cutting at y equal to 1, right. So let me put this equation here. This is the 8y equal to 8, or in essence y equal to 1, okay. And therefore this is what elimination does, right. It picks up one of the lines and aligns them parallel to one of the axes, right. Remember that we could have done elimination another way by cancelling out x, and that time we could have got a line which is parallel to the y axis. But since we are using this algorithmic approach, in this case what happens is that the second equation, which is this yellow line, has now changed to this green line which is parallel to the x axis. And the most interesting aspect is that it also passes through the same intersection point, which is 1, 3, right. And this can be actually proven. There is no difficulty in understanding this. So let me try and take these expressions and then try to prove this. So let's say take the first equation. Let's talk about the first equation on the left hand side. Let's say I have L1 equal to R1, right. So this is how I'm representing the first equation. Left hand side expression equal to the right hand side expression. Similarly, the second equation I can write it down as L2 equal to R2. Remember that we are doing some kind of row operations and we are trying to come up with this new equation here, right. So if you want, we can call it the third equation. Now let's do something simple here. Let's do an addition of these two equations. Let's see what happens. L1 plus L2 is the left hand side of the addition, and right side is going to be R1 plus R2, right. Okay. Now since we are adding up the expressions on equations that are equal, I can also put this, right. There is no issue of putting the equal to sign here. Therefore it means that L1 plus L2 is going to be R1 plus R2, okay. Remember that a point 1, 3 satisfies this equation. So if I substitute for 1 and 3 here, it satisfies this equation, which means that 1, 3 satisfies this. 1, 3 also satisfies L2 equal to R2, and therefore since we have this, which are all these are just part of expressions that are coming from these two equations, you will find that 1, 3 will also satisfy this without any issue. Now we can extend this and say, why don't I do, for example, let's say 2L1 plus 3L2. Well, this side is going to be 2R1 plus 3R2. We are trying to take any linear combination of the left hand side and the right hand side, and you will find that since 2, 3 satisfies L1 and L2, equal to R1 and R2, 2 times of that and 3 times of that will also equate to the 2 times of R1 and 3 times of R2, and therefore the intersection point will satisfy this expression as well. So what are we trying to achieve? We are saying that pick up any A times L1 and B times L2, which is essentially the row operation. The intersection point satisfies the new equation, and this is what elimination does. So it becomes more interesting in 3D, but in R3, but becomes a little complicated to understand and draw planes and try to rotate them. But we can understand in R2 quite easily. So it is just taking a line, one of the equations, and changing them parallel to one of the axes. Moment you align them with the axis, we got one of the values so easily. And the other one is quite easy to find because I have this now, I can easily find. So this is what a geometric representation of what elimination does in the case of a single solution, and what we are looking at is actually the row picture. Okay, now let me take you to the singular case. Remember we had two cases there, sub cases there. One did not have a solution, one had infinite solutions. So let me first pick up the no solution case and show you the pictorial representation of it. Okay, so here is the equations. Here are the equations. We have x minus 2y equal to 1 and 3x minus 6y equal to 11. Remember we tried and solved for this, and we found that the second equation actually changed to saying 0 equal to 8, right? Something like this it came. And we said this is not consistent, and therefore this does not have a solution. So let's plot this in the graph and look at the row picture, right? So look at the row picture here. So let's only look at two lines, the blue and the yellow lines. X minus 2y equal to 1 is represented by this blue line here. 3x minus 6y equal to 11 is represented by this yellow line here. And what do we find? That these two lines are parallel, right? And we can easily make out in the row picture that since two lines are parallel, they are not going to intersect at all, which means that there is no solution for these two equations. Great. What is another interesting phenomenon in picture representation is that in this case we can actually also look at the column picture. Let's look at the column picture. So here I have the vector which is 1, 3, another vector here which is minus 2, minus 6, another vector, the right hand side one is a 1, 11, right? So let's look at the diagram in green here. That's the column picture. This is 1, 3, the vector 1, 3, minus 2 and minus 6, here the second vector, the right hand side vector is here 1, 11, right? And remember, what do linear system of equations mean when looking at the column picture? What does it mean? It means what are the scalars whose linear combination, right? These vectors linear combination, which are the scalars I must choose, x and y, so that it gives me the right hand side vector. Remember that this is how we talked about this, right? So you look at 1, 3 and minus 2, minus 6, and there is something interesting that's happening. We find that they are falling in the same line, or if we want to say, they are just in their opposite directions, and any linear combination of such vectors can only produce vectors on the same line, and this is what we had seen much earlier. And therefore, what does it say? You may struggle to move on this direction and this direction. That's what we understood as linear combination, right? Move on 1, 3 and move on minus 2, minus 6 and try to reach 1, 11. We will never be able to do so, right? How much ever we walk in these two directions, we cannot reach 1, 11. And the column picture says the same answer, that there is no solution, right? Same thing, right? We are still coming with the same answer saying there is no solution. Okay, let me now change this value here. Say that instead of 11, let me make it 3, right? This was another case that we attempted to solve, and we got that the result of elimination said that this will produce infinite solutions. Okay, let's look at this diagram. X minus 2y equal to 1 is this line. 3x minus 6y equal to 3, what's going to happen now is this line is simply going to move like this and merge with the same line x minus 2y equal to 1. Therefore, there are no two lines at all. Each of the lines is overlying on the other. Oh, what does that mean? It means that there are too many intersecting points because there are infinite points on a line. And therefore, these two equations come up with infinite solutions. And that's the row picture. Please try and see what happens to the column picture. In the column picture, we have the vector 1, 3 here in green, minus 2, minus 6 here, this side in green, and the right hand side is not 1, 11, we have this vector again 1, 3, right? And where is 1, 3 here? And very easily we can walk to 1, 3 just by using the same our vector 1, 3. Okay, that's one solution. Can we try and produce one more solution? Yes, we can. I could walk all the way to minus 2, minus 6, come back and then walk 1, 3. That's another solution. Okay, what else can I do? I can walk 1, 3 twice and then come back by 1, 3 once, and therefore I will reach 1, 3. I mean, there are umpteen number of solutions, which means that again the column picture tells us that we have got, for this case, there are infinite solutions. Let me just write it clearly, right? And for this case, there are no solution. And therefore, it is always good to look at the diagram and try to understand what the linear system of equations are actually representing, right? I hope that this gives a clear picture. Okay, there is one thing that I thought must arise as a question at this point. So let me go to this previous diagram here. Now what I have kind of done is I have depicted the row picture, but very comfortably I have not shown you the column picture at all, right? Why didn't I show the column picture here if I was able to show the column picture in the other two cases, which are singular cases? Okay, so here is the answer. So you look at the columns here, 4, 3, minus 8, 2, 4, 11, etc. When we do a row operation, the columns are getting broken. I'll tell you why they're broken. If we are able to take column as a unit and perform operations on them, and column as a unit has changed to some other unit, then we will be able to represent this, represent and draw the column picture here, and we will be able to appreciate it. But what happens in row operations is that we keep one equation same and we change the second equation to the third one here, which means that we are breaking up a column into two pieces and we are acting on it individually, and therefore the picture does not make sense here. We should not try and understand a non-singular case using a column picture, because it really does not make sense, because the transformation of row operations does not work on columns, they work on rows, and the moment they work on rows, and that too on individual pieces like this, what would happen is that the column picture gets broken, right? And that is the reason why we did not draw the column picture for this case. If we go to the other two cases, which is the singular cases, we are still able to draw row and column picture. Reason is because remember that I still did not use the second equation and try to show you the column picture. All that we are saying is simply by looking at the column picture from the original equations, which is in green here, we are able to appreciate and identify that either we get no solution or we get infinite solutions, right? So that is in essence the strategy of elimination and what it actually does to the linear system of equations. Okay, so before we wind up this session, there is one last set of equations that I would like to show you and try to ask you what happens in this case. So here are two equations. Let's say I have 0x plus 2y equal to 4, and suppose it's given 3x minus 2y equal to 5, right? Suppose we have this set of equations and we are asked to do elimination. The first thing that must strike us is there is no pivot, and if we try to eliminate this as an algorithm, right, remember that this algorithmic approach, our elimination strategy is to somehow eliminate this 3, and if we try and do the multiplier, right, it's going to be this coefficient divided by the pivot, and there is no pivot, and now you see this problem, right? So what do we do in this case? What we do is called a simple row exchange, right? We do a row exchange, which means we just call the second equation as first and the first equation as the second. So what we do is we just shift them across. We say let it become 3x minus 2y equal to 5, and let this become 0x plus 2y equal to 4. And the moment we write this, we see that we have the pivots in place now. In fact, it's got two pivots, and what does that say? This is a non-singular case. This is a non-singular case, and it has one solution, right? Remember that when we looked at it like this, there was a lot of confusion of whether it had a solution or not, whether it's singular or non-singular. But the moment we had a row exchange here, we are able to find out and see, right? Moment there is no more elimination required. All that this is already done. It's already in the upper triangular form, and we know that since there are two pivots, it leads us to a non-singular case and there is one solution. Okay, we can figure out the solution, but that's not important. So this is a pretty simple example in 2 by 2 case, but it becomes more interesting when we go to 3 by 3. Maybe we can pick up a few problems and then try to solve using elimination. Right? So let us end this session with a prayer. Shanti Shanti Shanti.